Hello, my name is Jacqueline Harris and I will be participating in Challenge 2011. Today, I will be speaking to you briefly about the combined gas law. The combined gas law combines three gas laws into one: Boyle's, Charles, and Gay-Lussac's laws. Before we talk about the combined gas law, however, let's explore the three individual laws first. Boyle's law describes the relationship between the volume and the pressure of a gas when the temperature and amount are constant. If you have a container like the one shown and you decrease the volume of the container, the pressure of the gas increases because the number of collisions of gas particles with the container's inside walls increases. Mathematically, this is an inverse relationship, so the product of the pressure and volume is a constant, where PV equals K. If you take a gas at an initial volume V1 and pressure P1 with amount and temperature still constant, and change the volume to V2 and pressure to P2, you can relate the two sets of conditions to each other by the equation P1 V1 equals P2 V2. In this mathematical statement of Boyle's law, if you know any three quantities, you can calculate the fourth. Charles's law describes the volume and temperature relationship of a gas when the pressure and amount are constant. If a sample of gas is heated, the volume must increase for the pressure to remain constant, as shown. There is a direct relationship between the Kelvin temperature and the volume. As one increases, the other also increases. Mathematically, Charles's law can be represented as V over T equals K, where K is a constant and the temperature is expressed in Kelvin. Again, if there is a change from one set of volume temperature conditions to another, Charles's law can be expressed as V1 over T1 equals V2 over T2. Gay-Lussac's law describes the relationship between the pressure of a gas and its Kelvin temperature if the volume and amount are held constant. The figure shown represents the process of heating a given amount of gas at a constant volume. As the gas is heated, the particles move with greater kinetic energy, striking the inside walls of the container more often and with greater force. This causes the pressure of the gas to increase. The relationship between the Kelvin temperature and the pressure is a direct relationship. So, P over T equals K. The mathematical equation for Gay-Lussac's law is P1 over T1 equals P2 over T2. In our discussion of Boyle's, Charles, and Gay-Lussac's laws, we held two of the four variables constant, changed the third, and looked at its effect on the fourth variable. If we keep the number of moles of gas constant, that is, the amount, so no gas can get in or out, then we can combine these three gas laws into one, the combined gas law, which can be expressed mathematically as P1 times V1 over T1 equals P2 times V2 over T2. In this equation, there are 6 unknowns. Given any 5, you should be able to solve for the 6. Let's look at a situation in which two conditions change. Suppose a balloon has a volume at sea level of 10 liters at 760 torr and 20 degrees Celsius, or 293 Kelvin. The balloon is released and rises to an altitude where the pressure is 450 torr and the temperature is negative 10 degrees Celsius, or 263 Kelvin. You want to calculate the new volume of the balloon. You know that you have to express the temperature in Kelvin in the calculations. It is perfectly fine to leave the pressures in torr, however. It really doesn't matter what pressure and volume units you use, as long as they are consistent in the problem. The pressure is decreasing, so that should cause the volume to increase. The temperature is decreasing too, so that should cause the volume to decrease. Here, you have two competing factors, so it is difficult to predict the end result. You'll simply have to do the calculations and see. Using the combined gas equation, solve for the new volume, or V2. Now substitute the known quantities into the equation. You could substitute the knowns into the combined gas equation first, and then solve for the volume, whichever way is easier for you. Note that the units cancel, leaving the desired volume unit of liters. Overall, the volume did increase, so in this case, the pressure decrease had a greater effect than the temperature decrease. This seems reasonable looking at the numbers. There was a relatively small change in the Kelvin temperature compared to a much larger change in the pressure. Well, that's the combined gas law. Thanks so much for watching.